Good morning, everybody. Welcome back. Yesterday, I realized that the homework due dates were wrong. So chapter 13, I may or may not get through chapter 13, but I wanted to give you time for chapter 13 homework. Chapter 13 is not due this Saturday. It's due next Saturday. Problem being is that chapter 14 is due the following Wednesday. Why? Exam, right? So I'm sure Canvas notified you and all that kind of stuff, but be aware of that change. All right. We had done a couple of Kepler's laws, right? And discovered that Kepler discovered conservation of energy long before we had known it was even an idea or concept. I do want to point out just a couple of things, partially in review, but to clear up some misconceptions, because I think it's a travesty that anybody goes to a physics class and doesn't learn these things. Number one, where is the planet or moon or anything that's orbiting, where does it move the slowest? The furthest away, right? Okay. So if the Earth is going counterclockwise in this orbit, right, like a kind of a top view, and it's moving towards the sun, is it speeding up or slowing down its orbital velocity? It's speeding up, right? And then as it comes around the sun and starts going away from the sun, that orbital velocity will decrease. So there are changes in orbital velocities. Again, can we look at the orbit of a planet with the naked eye and say that it's an ellipse? No, it looks pretty circular to the naked eye, right? So this is very definitely an exaggerated depiction of what's going on. When are we closest to the sun? Like what time of the year are we closest to the sun? That is wrong. We are actually closest to the sun in January. What? Right? Because January is what time? It's winter time. It actually gets down to 60 in Fresno, right? Okay. But what causes the seasons? It's the tilt of the Earth's axis with respect to its orbital plane. It is not the distance we are from the sun, okay? The distance we are from the sun in our orbit changes by a few million miles, and you're like, wait a second, that's a big number, right? Well, when the orbital radius has an average of 93 million, right? Million here, million there isn't going to make that big of a difference in terms of the amount of power that the sun can dump on the surface of our planet. No, it's the tilt of the Earth's axis that makes all the difference. So I'm going to use my water bottle here as an example, okay? So this is not in the book. I don't think they describe the seasons. But again, I think everybody who comes through a physics class needs to learn this. So the Earth's spin axis, right, is not straight up and down with respect to its orbital direction, okay? The Earth's axis is tilted, okay? 26 point something degrees, okay? I'm going to over-exaggerate and just tilt it at 45, right? So let's say the Earth, right, again, it's rotating around an axis like this that is tilted, okay? But it's going around the sun. So you are going to be the sun, okay? So when you look at this bottle, you see kind of the whole side of the bottle, don't you? Okay? Well, remember conservation of angular momentum? Something that's spinning, right, on its axis wants to keep that axis aligned in the same direction. It needs a torque in order to change it, but there's no torque on Earth. But the Earth is orbiting around you, the sun, right? So if we come over here, quarter of a year later, what part of the Earth do you now see? You're looking at the top, right? The northern hemisphere up here, right? Notice you've switched from seeing it that way to seeing it this way, right? And if I come around, so we're a half year away from where we started, and we're here in the back of the room, now how do you see the Earth? Sort of side on again, right? And if I keep going, and we go 3/4 of a year around, Now, which side of the earth do you see? You see the bottom, right? And if we come back full year around, right? Now we're back to where we started and we see the whole side, right? When you are side on, that is called an equinox. It's a point in the Earth's orbit when the northern and southern hemispheres are getting the same amount of sunlight. And there's two of them, right? But then you get to what's called a solstice, where one or the other part of the Earth is facing the sun. So in the northern hemisphere, when we have our summer, the northern hemisphere is more directly pointed towards the sun, and the southern hemisphere is not. Okay? Reverse that, when we go into our winter, right? The northern hemisphere, if you're the sun, you see how the northern hemisphere is pointed away from you, but the southern hemisphere is more directly pointed at the sun. When you take a flashlight, can you guys see the sort of the shape of my flashlight on the glass board here? Okay, I'm like directly pointing it at the board, and you can see the white area where my flashlight is landing. If I tilt that, what happens to the area that my flashlight beam is now taking up? Direct concentrates the flashlight beam in one area, but if I tilt it, it kind of starts spreading it out. Do you see that? The sun outputs the same amount of energy every second. The sun is very consistent. But if we change the angle at which that sunlight hits, and that energy gets spread over a much bigger area, then that intensity is what that's called. Okay? The intensity of the light goes down. So in our winter time, a lot of people will talk about how the sun feels weak. Well, did the sun change its power? No. What changed? The angle at which the sunlight is hitting the surface of Earth. Okay? As we go into summer, we start feeling more and more heat, and we get more and more direct light. Okay? Then we start feel like it's the sun's energy is concentrating in our summertime, and it gets spread out in our wintertime. Now, of course, if we move into summer, what's going on down in the southern hemisphere? Winter, right? So Santa Claus in the southern hemisphere wears shorts. Why? Summertime when it comes to Christmas, right? So you'll notice as we go throughout the year, like when we started here, the sun would kind of shine like directly through this window, right? Okay? We started in January, right? And the solstice is like the end of December 21st, 22nd, something like that. So we had the sun kind of low in the southern part of our sky, and the light could come through this window. As the year has gone on, the sun has got higher and higher in the sky, and we're heading towards the other solstice. We passed through the equinox in March, and June, I didn't look up the date, 21st, 22nd, somewhere in there, we're going to hit a solstice, right? And that's the point where the sun will be highest in our sky, and then it's going to start its march back towards its southern end. So yeah, the sun moves, the earth moves, everything moves, but why do seasons happen? Because of the tilt of the Earth's axis, okay? Has nothing to do with how far away from the sun that we are. Go out, teach the world. Okay, back to Kepler's laws. So I introduced Kepler's third law very hurriedly at the end of class, and it's a train wreck, isn't it? Like everything, it's bad, okay? So a lot of physicists like to rewrite this just slightly so that it doesn't look, it's still as bad, but it just doesn't look as bad, okay? Now, things to note. What is this right here? For all practical purposes, what is that? Think abstractly. Is it a known or unknown thing? It's pretty known. We know what 4 is. We know what pi is, right? Okay, we know what big G, those are all numbers, just constants, right? About the only thing that could change in there would be like the mass of the sun. I wrote it as mass of the sun because I was using the example of Earth going around the sun. But it turns out that Kepler's law is good for any object orbiting another. So to have an orbit, you need to be going around something else, okay? So another way to write Kepler's third law, maybe slightly more cleanly, okay, is to square both sides effectively, okay? So this is generally how, like, physicists will write this, okay? And we'll just put big M down there for now. And instead of r to the, so the 1/2 goes away because we squared both sides, right? What's the other, what happens to the r to the 3/2 if we square it? It just becomes r², right? So this one here in blue, okay, is kind of generally how it's written. It just, if you want to solve for the orbital period, the time it takes for something to go around something else, you've got to take a square root, right, to solve for this t. So pick your poison, right? Blue box, red box. Put the red box on there. Okay. Those are the same thing. I just don't like having to write 1/2 all the time. And a lot of physicists don't either. Okay. Notice I didn't write mass of the sun down here. I just wrote big M. So if we have a spacecraft in orbit around the moon, what mass are we going to put in here for Kepler's third law? Is it the spacecraft or the moon? It's the moon, okay? If we are trying to get in orbit around Saturn, what mass are we going to put in here? Saturn's mass, right? That big M is supposed to be a giveaway. It's a clue to when you're applying Kepler's third law, the mass that goes in there is not the mass of the thing orbiting. It's not the mass of the spacecraft, right? It's the mass of the thing that's being orbited. The big gravitational thing that you're trying to solve the orbit for. I don't know if I made that very clear or not, but with Kepler's third law, you want to put the mass of the thing that's causing the orbits to happen, not the thing that is in orbit. So if we want to find the orbital period of the Earth, what mass do we put into Kepler's third law? The sun's mass. It's kind of weird, right? You got to ask yourself the question, well, what's the Earth orbiting? If we want to find the orbital period of the International Space Station, what mass do we put in there? The Earth's mass. If we want to find the orbital period of Phobos, one of the moons of Mars, what do we put in? Mars's mass. Are you getting kind of the idea there? Right? So, yeah.
What if the masses are equal?
Yeah, then you've got a problem. Because so this Kepler's third law assumes that the thing being orbited is very much bigger than the thing orbiting. Okay? In truth, the center of our solar system is not the sun. It's a little bit inside the sun. So it's not the center of the sun. It's a little bit off from the center of the sun. It's called the barycenter. The barycenter is a fancy word that means like the point around which all things are orbiting. So the barycenter of the Earth-Moon system is not the center of the Earth. It's a point still inside the Earth, but much closer to the surface. The Earth kind of orbits, in the Earth-Moon system, it kind of doesn't orbit around its center, it orbits around the barycenter. So if you have equal masses, the point that they are orbiting is a point right in between them. The barycenter wouldn't be inside one of the planets. It would be a common point in space that they are both going around. So yeah, once you start getting equal masses, you kind of have to do something a little bit different, and we'll talk about that later. Okay, so how do we apply it? So what I want to do is I want to go to Proxima Centauri. Okay, Proxima Centauri is a star system. The Proxima, what is that like Latin? Get your Latin on. What does Proxima mean? Close. It's the same root as proximate, right? Or approximately, meaning I'm kind of close, but a little bit off. So Proxima Centauri happens to be the star system that is closest to our star system. Okay, we are the Sol system, S-O-L for sun, and this is Proxima Centauri. This is a artist's conception. Okay, Proxima Centauri B is that star right there. It's the second in the system. Okay, it's a kind of few stars together, right? This is a planet that is orbiting Proxima Centauri b. We have detected this planet and we've made some measurements, but we can't see it this clearly. This is an artist's representation of what Proxima Centauri might look like based on the data we've got. We think it's a rocky world. There might be liquid water on its surface. It's kind of far enough away from Proxima Centauri b to have it, but we haven't detected it. Okay, so Proxima Centauri b, right? This planet. Okay, second planet out from the star. Proxima Centauri is a very low mass star, almost a red dwarf. Our sun is what we call main sequence star. It's kind of average. Actually, we're on the kind of the low end of average for stellar mass and longevity and all that kind of stuff. Those of you that are worried about the sun burning out, you're going to have to wait for about another 5 or 6 billion years for that to happen. Okay, but if you really want to do doom and gloom, in about 1 or 2 billion years, the sun is going to enlarge itself. It's going to start running out of certain kinds of nuclear fuel, and its outer edges are going to grow, and it's going to take out Mercury, Venus, maybe Earth, right? So make sure you're on Jupiter by when that happens. Like I said, 2 billion years. You got a little bit of time to, for scale, how long has Earth been around? 4.5-ish. Okay, so roughly half the lifetime of the Earth from now. Okay, how long have like living things actually been out of the water on Earth? 400 million, just 500 million years. Okay, so just kind of giving you some time scales there about what you have to worry about. How long has Facebook been around? 0. Okay, on that time scale. So, all right. So we're around Proxima Centauri b, okay, which means hopefully we're in some sort of spacecraft. Spacecraft need names, right? So what's the name of our spacecraft? The what? The Ford Bronco, the USS Ford Bronco. I like it. All right, this is good. We're going to go with it, okay? USS Ford Bronco's in an orbit around the Earth, right? We have the orbital period measured in Earth time, okay? We need a picture, okay? So apparently we're in this spacecraft that can get us to the closest star system in some period of time, but apparently our spacecraft can't determine the mass, right, of Proxima Centauri b, which is an interesting conundrum to have. It's like Star Trek, right? They have all of these fancy ships, but they still don't have seatbelts. Anyway, picture. So let's be a little bit careful. We'll get the AIs to help us. There we go. Circle. Okay. So our spacecraft, and again, I always draw spacecraft to look like a TIE fighter. Okay. Our spacecraft they give us a distance, don't they? The 7,500 kilometers. Where does that start? Where does that end? It starts at the core and it goes out to where our spacecraft is, right? So that distance right there is 7,500 kilometers, right? 7,500, okay? However, they told me that my altitude, because I wrote the problem above the surface, just to reiterate that altitude is measured from the surface, is 500 kilometers, right? So we know that this distance right here is 500. Do we know anything about the radius of this planet? Yeah, what's the radius of the planet? 7,000, right? So make sure that you know what the distances are, right? If it says altitude, it's measured from the surface. If it says anything else, it's measured from the center. All right, so that's a little bit of sleuthing we had to do, okay? They've given me this time. So this is an example of using Kepler's third law, which I'll go ahead and write in my cleaner form for now. And we'll get to solving other things in a second. Okay, so there's Kepler. So what could I know and what could I not know? The orbital period, the big M, and the R, right? Do I know the orbital period? Yes. What does it say the orbital period is? 1.57 hours. Okay, there's a problem with that number. We'll get back to it. Do I know the mass? What mass? What mass am I going to use in Kepler's third law? Yeah, the mass of Proxima Centauri b. Why is it the mass of the planet? That's what we're orbiting, right? Our spacecraft is in orbit around Proxima Centauri b. So, but do they give me that mass? No. Okay. Do I know the radius of my orbit? Yes. It's 7,500. Boy, that was sloppy. Kilometers. Okay. There are problems with both the period and the radius. What are the problems? Units. We need to make sure the hours are given in what? Seconds. And we need to make sure the kilometers are given in meters. The kilometers is pretty easy. 7,500 kilometers instead of the K, what do you write? Times 10 to the 3, right? And there, boom, we've converted into meters, okay? The hours, we got to do just a little bit more work. And by a little bit more work, I mean go back to chapter 1, right? 1.57 hours, put hours on the bottom. How many seconds are there in an hour? Nope, try to guess again. 3,600, right? It's 60 minutes, and in 1 minute there are 60 seconds. What's 60 times 60? 3,600. I don't like having to write two conversion factors, so I just remember one of them. Okay, did I do this? I did. I got 5,667. Okay, so I now know my orbital period in seconds. I know my orbital radius. What are we solving for? The mass. Okay, so what's the plan? Yeah, solve Kepler's third law for mass. This is what I call the brute force method, okay? You just go for what you need, find it, okay? So we organized our information. If I solve this for big mass, right, it's going to be 4 pi squared over big G period squared R cubed. We've got all those numbers, don't we? So big mass, it's going to be 4 pi squared over 6.67 times 10 to the minus 11 times 5,667 squared. And then my R cubed on top. R is 7,500 times 10 to the 3 cubed. I wish you the greatest of luck in getting your TI calculators to handle this one. Be careful with your parentheses, right? Make sure your TI calculators get it right, okay? It's very easy for TIs to get this wrong. You end up, instead of dividing by 5,667 squared, you end up multiplying it, or the squared gets applied to something else. Be very careful with your parentheses. Okay, when I did this, I got 7.77 times 10 to the 24 kilograms. Okay, so like if we compare that to Earth, does anybody remember what Earth's mass was? That was big G. Earth's mass, 5.98 times 10 to the 24. So what can you say about Proxima Centauri b? It is more massive, but not by much, right? So it has more mass. However, it also is slightly bigger, isn't it? Earth's radius is 6,370 kilometers. This one's 7,000 kilometers for its surface. So we tend to call planets like this one Earth-like planets, right? They are roughly the same size. They have roughly the same mass, right? And to be completely Earth-like, they would have to orbit the habitable zone of the star that they are around. There's a zone, a distance away from a star in which liquid water can exist. If you're too close to the star, what happens to the water? It boils. It turns into water vapor. No bueno, okay? If you're too far away from a star, what happens to the water? It freezes, making fires kind of hard, right? But when you have liquid water, not only can you generally make fire if there's enough oxygen, but you can also sustain what we consider life to be, right? We don't have any other data point. We've got one data point when it comes to life, right? And life on this planet needs liquid water in order to happen. So we're looking for stars that are in their habitable zones and have mass and radius roughly similar to Earth if we want to have any chance of being able to use that planet as a second home. And this one seems to be fitting the bill. Okay, so we've got some additional questions here, right? What is the mass? We found the mass. If an object weighs that much on Earth, what would its weight be on the surface of Proxima Centauri b? Okay, what do we know about weight? It's a force. What force is it? Like mathematically, how do we find the weight of something? mg. Or now we know the big thing, but like let's just start right here, okay? What's the thing that doesn't change? What's the thing that's the same whether we're on Earth or the moon or Proxima Centauri b? Mass, right? So if we're going to find how much something weighs on the surface of Proxima Centauri b, we need to know the mass of the object, and then we need to know the local gravitational influence of that, where we are, right? Because weight's all about the force of gravity. So let's find the mass of our 560 Newton object. Well, we can do that. It's the force divided by acceleration on the surface of planet Earth. So 560 newtons all over 9.8 meters per second squared is going to give us a mass in kilograms of 57.1 kilograms. Okay, now we know the mass, and we know the mass isn't going to change no matter where we go in the universe, unless they go on a diet, okay? This would be a small person. This is like a child. So now, if I want to know how much this object weighs on the surface of Proxima Centauri b, what do I have to do? Okay, we can use the universal law of gravitation, right? So let's just what if this right here, right? So the universal law of gravitation, big G, M, and like M1, M2, all over distance. Okay, so we could do that, right? We now know the mass of our object. We know the mass of Proxima Centauri b, and do we know the distance that they are from the center of Proxima? Yeah, it's the radius of the planet, right? Okay, so we could do that. It's fine. I'm not going to do that. I want to do something more fun. We found the weight, we found the mass by using the weight and little g on the surface of Earth. Can we find the weight of this object if we find little g for the surface of Proxima Centauri b? So this is going to be a 2-for-1. Not only am I going to find what this thing weighs on Proxima Centauri b, I'm also going to find the surface gravity of Proxima Centauri b, so I can get an understanding of whether or not I'm going to want to like go there and stand there and do anything, right? So how do we find little g? Where did I put it? I put it right here. Remember how we could find little g no matter where we are? That red thing down there in the bottom, right? Big G, not mass of the Earth. What would I put in there? Mass of Proxima Centauri b, right? And instead of radius of the Earth, I would put in radius of the planet, Proxima Centauri b. Okay, so let's do that. It was, I don't even remember what I put down. Big G m over r squared, was that it? Yeah, okay. So, big G, 6.67 times 10 to the minus, I of course did not leave room for me to write here. 7.77 times 10 to the 24. And by the way, everything in green is basically the same thing. It's just how you want to break it up and think about it. 7,000 times 10 to the 3 squared. And when I did this, I got G on the surface of Proxima Centauri b of 10.58 meters per second squared. So before we go and find the weight, which is boring, what does this mean? A little g on the surface of Proxima Centauri b of 10.6. What does that mean? It's a larger gravitational force, right? Are you going to feel heavier or lighter on the surface? You're going to feel heavier. How much heavier? Little bit. Because twice as heavy, what would the number be? Like twice as heavy as Earth. It would be like 18-ish, right? Almost 20, okay? So it's not that high. We're not going to feel twice as heavy. We're going to feel like, what is that, like 15% heavier? 12% heavier, something like that, okay? So could you walk on the surface if you landed the spaceship on the surface and stepped out, could you walk? Yeah, and probably within a day, you wouldn't notice the difference. And you would be a little slightly buffer. Well, let's answer the question, right? The weight on the surface of Proxima Centauri b is going to be the mass times the acceleration due to gravity on the surface of Proxima Centauri b. And when I put those numbers together, I got 604 newtons, right? Mass doesn't change, but the weight does, and sort of what we experience as we go there. So like this 57 kilogram object, maybe it's a box or a crate of supplies or something, it would, like when we go to lift it, would feel heavier, right? So, but only 12 to 15% heavier. I don't know what the actual percentage is. It seems like it's in that range. Okay, so again, this is what I call kind of the brute force method of applying Kepler's third law. There's three things. There's period, there's orbital radius, and there's the mass of the thing being orbited. You're going to be given two of those things. Find the third, right? It could involve a cube root, but calculators know how to do cube roots, and that's not too much of a problem. Oh, by the way, I should have maybe told you this at the beginning. We are not going to Proxima Centauri b anytime soon. The fastest human-made object that we know of, that we are certain of, is the Parker Solar Probe. I believe it's going, oh shoot, I forgot to look up its current, not its current, but its peak. Parker Solar Probe, fastest speed. 364,000 miles an hour, or 163 kilometers per second, okay? So at that speed, it would take roughly, I kind of calculated this out once, about 30,000 years to get to Proxima Centauri b. Proxima Centauri b is 4.2 light years away from us, so it takes light 4 years to get. You send a radio signal to Proxima Centauri b, right? It takes 4 years. The TikTok you send is going to be old by the time it gets there, okay? But 4 light years sounds like a small number. It is a huge distance. And our fastest man-made object Would take about 30,000 years to get there. Okay? So, we're not going there anytime soon. Other spoiler or other bummer, it appears Proxima Centauri b is bathed in radiation. Okay? The star it is orbiting around is because it's low mass, Proxima Centauri b's orbital radius is kind of close. It is in the habitable zone, I think, but the problem is that habitable zone is so close to the star that solar flares and other things that stars do bathe the surface of this planet in radiation. And so if there is life there, it's very glowy. Yeah, not a good place for us. So, but there are other candidates out there that seem better. If you're interested in any of that, then you might want to just do some searches about exoplanets. Exoplanet means a planet that's outside of our solar system. And there are candidates that are favorable not only for like life, but life as we understand it, right? Carbon-based, needs liquid water. That's a little bit of a caveat there because we don't know if life can do other things, right? We understand life needing carbon chains and that kind of thing. But maybe silicon would work. I don't know. Watch Star Trek. You'll figure it out. Okay, so can't believe I just said that. All right, I want to do a different calculation with Kepler's third law. And to do this sort of alternate way to approach Kepler's third law and use it, I want to show you some real-time data, okay? The URL for this one is down on the bottom of the screen. So let me switch to the live version on my computer. Oh, I got to do this first, sorry. So many buttons to push. Let's get that down. And let's bring this one up so that you guys can see it. Entire screen. Okay. There we go. Okay. So what you are seeing right now is a simulation. This is not, but every dot on this screen comes from the database of objects we currently have orbiting planet Earth. Okay? I believe this particular simulation is showing us like spacecraft. It's not showing every piece of like junk. I think some of the bigger, I think this goes down to roughly like meter cubed sort of volume of spacecraft. There are other pieces that we track that are much smaller of debris and things like that. Why would we want to know the orbital parameters of bolts and other things that maybe astronauts have dropped and stuff? Because it can destroy our craft. Yeah. We don't want that bolt coming back and going through the International Space Station, right? When you're orbiting at roughly, what is it, 10, it's 8-ish, no, 7-ish kilometers per second, 7,000 kilometers. When you're orbiting at a speed that can take you from New York to Paris in about 8 minutes, you really don't want to run into a bolt. Just saying. Okay, but this is, okay, so it's based on real data, right? You can see that our camera, like we're orbiting the Earth much faster than it normally would go, right? But the camera is just sort of changing our point of view. And every one of these dots, as a mouse goes over it, indicates the orbital path of something, right? Whatever that thing happens to be. Why am I showing this to you? Let me zoom this in and out, okay? So you can kind of get an idea, right, of what's going on around the surface of our planet. Do you see that there's like a halo, right? There's a definite ring out here, isn't there? Okay, a spacecraft. There's definitely something going on out there. But that ring is really far away, really far away. To find things like the International Space Station and all of the satellites that are part of Elon Musk's empire and all that kind of stuff, we really have to zoom in close. This is called low Earth orbit. Do you see this? Do you see all the red dots, okay, that are here close to the surface of planet Earth? This is the Hubble Space Telescope. These are the Starlink satellites. These are International Space Station, all of those kinds of things, right? As a matter of fact, you can go up here and search. Is ISS in here? Yeah, okay. So here is the ISS, the International Space Station's orbit, right? Feels so far away up there at 300 and whatever kilometers, 420 kilometers, okay? So that seems far away. I'm talking about a ring, right? Way out here. Okay? We want to know what's going on with this big, huge ring of satellites that are way, way out there. We want to get out of LEO, low Earth orbit, to see more interesting things. Let's see, is mine still? Okay. This is my favorite. Look at that orbit. Yeah. Right? Okay. Not only is that orbit just like amazing, okay, but this is my satellite. This satellite contains things in it that I touched and assembled and put together as part of my undergraduate and graduate work, okay? I worked on a project. We had to make the coatings that went on the mirrors that were part of the X-ray telescope that is on this satellite, okay? And then it got put into this orbit right here, which is not a circular orbit, right? I mean, this orbit is very elliptical. I was so excited when I learned the orbital parameters of our project, okay? Notice how it comes really, really close down here, okay? Originally, it came really, really close at the South Pole, okay? And then goes way the stink out here, okay? I don't know if you can see it on the screen, but there's gray dots kind of right here. They're all washed out here. But it goes way past that halo that I showed you earlier, okay? Right? And then, so the reason for this is the satellite I worked on, we were taking pictures of the Earth's magnetic field, and we wanted to get way, way away from the Earth to get like a really big sort of big picture of what's going on with the magnetosphere, because the magnetosphere goes way out. But we also needed to do that, to get out there that fast, we also had to kind of trade, because there were other instruments that wanted to look up close at what was going on with the aurora, okay? And so to do that, we were able to go close down near a South Pole, but then get really far out near the North Pole. This was 20 some odd years ago, so the orbit has changed a little bit. It used to be a lot more sort of straight up and down, North Pole to South Pole. But yeah, that's my favorite. Okay, and you can see it's like it's one of these that's way, way out there, right? Compared to this sort of ring, and that ring happens to be kind of situated where? Yeah, around the equator. Okay, so this is a very special orbital ring that we need to figure out. Okay, let me fix all of this. I gotta get a shortcut for this. Okay, so it's called the geostationary belt. Okay, this is kind of an older diagram that doesn't depict the actual orbits, but gives an idea of the kinds of things that are in the geostationary belt, the different satellites. You'll notice that there's kind of a blank spot over the Pacific Ocean. So that's kind of a hint as to what this belt is actually for. We're stacking up a lot of satellites over North America, lots over Europe and China, but like we get over the Pacific Ocean, there's hardly any satellites out there, okay? So what we're going to do, using orbital mechanics, Kepler's third law, we are going to find the orbital radius of a geosynchronous satellite. So the geosynchronous is a word that means that the satellite has the same orbital speed as the surface of the Earth. Now, the surface of the Earth is not in orbit, but how long does it take a point on the surface of the Earth to go around once? 24 hours, right? A geosynchronous satellite has an orbital period of 24 hours. So from our point of view, like if we look up at a satellite, right, and it's got an orbital period of, well, the International Space Station, 90 minutes, okay? So it takes 90 minutes for the International Space Station to go around once, okay? From our point of view, what is the International Space Station doing? It's ripping, isn't it? Right? This is like, whoa, right? It's going fast. In fact, if you go out on a fairly dark night, so i.e. not Fresno, get away from Fresno, okay? Go out to the fields or go to the mountains or something, right? And get a clear view of the sky. You'll see satellites going across. There'll be faint points of light that just kind of move, okay, at a pretty steady clip. It's not, if it's blinking, it's an airplane, okay? So you'll see this dot of light is just kind of very faint going across the sky, okay, usually fainter than the stars. And you'll see them. They're out there. But they're all moving with respect to us. If a satellite has an orbital period of 24 hours, then from our point of view, what is that satellite doing? It stays in exactly the same spot, right? We are going around at 24 hours. It's going around in 24 hours. So we're locked in with that satellite. Why would we want a satellite to stay at one spot in the sky? Because, and now I'm going to date myself, because I want my MTV. It's true. MTV is not what it used to be. But if I need to communicate via satellite, what do I not want that satellite to do? Go below the horizon, right? Okay? I want that satellite to stay in one place, right? Whether it's phone, whether it's TV, whatever, I want it to stay in one place. The other way around, if I want to use a satellite to, say, check the weather and give me an idea of the storms that are coming, we don't want that satellite moving. We want that satellite to be taking a picture of the surface of the earth from one point of view, and we want to watch the clouds go places, right? So weather satellites, communication satellites, those are the kind of things you want to do in geosynchronous orbit. Not Starlink. I'll talk about that in a second, okay? That's different. And not spy satellites. Again, I'll talk about those in a minute. Let's find the orbital radius of a geosynchronous satellite using a physics trick, a sleight of hand, a way of thinking about Kepler's third law, which again is a bit of a train wreck, isn't it? In terms of like, it's not terrible, but come on, there's better, we could be doing better things. So let me show you the better thing. This is a trick you can use if you can compare the orbits of two objects that are orbiting the same thing. And what you do is you write down Kepler's third law twice. I know this sounds like twice the pain, but it's not. Watch. If I come here and I say, okay, I've got the orbital period of one object in orbit around a mass, and I know its orbital distance, and I form a ratio with the second object, a different object, that's a big G, again, and its orbital parameters, okay, and I just form that ratio there. What do you notice about all the junk that's in the front? It cancels, right? It's the same junk, right? So it's a constant thing for both of the orbits. Mathematically, I can just get rid of this whole thing. And what I end up with is the ratio of the periods squared is equal to the ratio of the orbital radii cubed. And as long as I know something about another object in orbit around the mass, I can find the orbital period or orbital radius of my second object. So this sort of way of writing Kepler's third law is very popular amongst physicists and engineers that do orbital mechanics, okay? Because it gets rid of the... Notice, where does this work? Any planet? Why? There's no math, right? There's no thing that ties it specifically to, say, Jupiter or the Earth, right? It's as long as you've got two objects in orbit around the same object, two planets around the sun, two moons around a planet, whatever, okay? This applies. It's nice. And I don't have to go look up in tables what the mass of Jupiter is. Okay, so how do I apply it? We're going to find a geosynchronous satellite. Okay, we want the orbital radius of a geosynchronous satellite. So I'm going to call object number one. What does my picture look like? I've got the Earth, I've got my satellite, right? Okay, so I'm going to find the radius of my satellite. Okay, do I know the orbital period of a geosynchronous satellite? 24 hours. Don't convert that yet. I'm going to show you a trick. Okay, now I need another object. Anything else in orbit around planet Earth that I know the orbital period and distance of. I mean, we got a lot to pick from, don't we? But one of them is kind of obvious and sort of sticks out. When the blank hits your eye like a big pizza pie, that's pizza. What is it? The moon. It's amore, but. All right, so the moon. Moon's going to be my second object, okay? Do I know the distance to the moon? Yes, I could find it out. Not going to right now. Do I know the orbital period of the moon? Do I know how long it takes for the moon to go around the Earth? Yes. It's 27 days. There's a decimal in there, but okay? All right. So what do I know, right? I know, so how do I get R1 out of this statement right here? This is what I want to solve for, right? It's my unknown thing. I know T1, I know the moon's stuff. How do I get this out? There's this cube thing here, so to get rid of cubes, you do cube roots, right? So, okay, so cube root, so that's T1 over T moon, and then this is to the 2/3, that sounds bad, right? Equals now R1 over R2. And so that means that if I just multiply R2 to both sides, right? And then I take these orbital periods to the 2/3 power, I will have R1. Okay, so R2 is the distance to the moon. T1. I said 24 hours. What's another way to write 24 hours? 1 day. And the orbital period of the moon? 27 days. What happens to the days? Cancels. Does it matter if I put them in seconds or not? No. My units went away. As long as they're the same unit, they're just going to cancel, and it doesn't matter how much I changed them. Okay. To the 2/3, oh my gosh. Okay, so what is 1/27th to the 2/3 power? So first of all, what does the 2 mean? Not square root, it means squared, right? And the 3 means cube root, right? Being on the bottom. If only 27 had a cube root, that was nice and even and didn't have a decimal in it. A cube root is like the same number multiplied 3 times. Is there a number that's the same that when you multiply it 3 times gives you 27? Yeah, what is it? 3. 3 times 3 is? Times 3 is? This is the reason I rounded that number. Okay, so it's 1/3 squared. What's 1/3 squared? 1/9. Right? So the orbital radius of a geostationary satellite ends up being 1/9 the distance to the moon. Which, when you go look up the distance to the moon, 3.8 times 10 to the 8 meters, you get an orbital radius for geostationary satellite of 4.3 times 10 to the 7 meters, or 43,000 kilometers. Now, that is the center of Earth to the satellite. So what's the altitude of a geostationary satellite? You subtract out the Earth's radius, right? And I didn't do that in my notes, so I don't care what that number is, but it's like 38,000 kilometers, 37,000 kilometers, 36 and change, okay? So 36,000 kilometers above Earth's zero. Where does the International Space Station live? Like 400 and something, right? This is 400. This is 100 times 5. Did I do that right? What's 400 times 10? 4,000 times another 10 is 40,000, right? This is 100 times further away from the surface of our planet than the International Space Station. And it's kind of hard to get there, right? It's difficult to get to the International Space Station. Imagine having to put a satellite in geostationary orbit, right? That's a big ask. So why is SpaceX putting all of their satellites down low? Yeah, it's cheaper. You can launch 40 satellites at a time, right, on a single Falcon 9 rocket, and deploy 40 satellites at a time instead of just, say, deploying one at a time. But the trade-off is, if you're going to do it in low Earth orbit, then you need to have lots of satellites, because a Starlink satellite is going to be moving across the sky at a pretty good clip, right? So your antenna receiving the internet signals and all the TikToks, the antenna itself either has to track the satellite by moving, like, right? But as soon as that satellite goes behind the horizon, what does the dish have to do? It has to find another one, right? Okay. And while it's tracking and finding another one, what happens to your internet signal? It's gone. Okay. So this is an engineering challenge that the engineers at SpaceX figured out. Number one, their dishes don't move. The dish is a flat, like, pizza box. Okay. And I've tried it out. It's pretty nifty. It just sits there, okay, angled at the sky. It doesn't move, but the satellites do. So to get the signal from the satellites, it does something called beam forming. It actually alters in the silicon of the dish the direction that it's tracking a satellite. But it still has the problem of it's tracking a satellite. Okay, satellite's gone out of field of view, behind a building, behind a tree, behind the horizon, whatever, right? Switch to next satellite. And it takes like a day or so, but the system will figure out like where all the blocks are, and it'll figure out the best way to beamform and which satellites are its best bet, okay? But there is always, like every 90 seconds or so, a little tiny blip where it's switching to a new satellite. My Starlink went back because I didn't want every 90 seconds my game interrupted by a lag spike, right? So if you're watching video, if you're doing email, it's not a problem, right? Because all of that information buffers. So in the time it takes the satellite to go back and find it, right, you don't notice it because you've downloaded a bunch of your video. You got 3 or 4 minutes of video, right, to get through before, it's got plenty of time. But when you're gaming and you're down to like 10 or 12 milliseconds, right, difference between what's going on the screen, it's a real problem. So for people that live in rural areas that don't have broadband internet access, Starlink is amazing, right? It connects so many parts of our world. Ships out at sea that have no contact for like 7 days, we now know where they are all the time, right? And they can communicate, distress calls, all kinds of stuff, right? I don't like the man, but boy, the technology, right, is incredible. And it's opening up things. I think Ukraine is still here because of Starlink, right? Without the internet access that they got right at the beginning of the war. If they hadn't had that and several other things, it would have gone really bad. So that's how they got around the limitation of satellites moving really fast. Okay, and I think they're at, is it 6,000 now? 7,000 satellites out of a 30,000 satellite constellation that they want to put up? Yeah, a lot of stuff. Okay. All right, let's do that. Orbital mechanics. Okay, what is orbital mechanics? Oh my gosh, I'm having way too much fun. This is too fun. I like this stuff too much. All right, need to stop talking and just do physics. So what we want to do, the goal here on this slide is to summarize everything we've done so far and put it together in a toolbox, right? So this is the orbital mechanics toolbox so far, things that we can do with what we have. I think a big major part of our toolbox, of course, has to be Kepler's third law, right? It really is the thing that, like, NASA uses this all the time. Now, this particular form that I've written here and I keep using assumes a circular orbit, right? A perfectly circular orbit. So our orbital mechanics are for circles only on this. Don't go to NASA and ask for a job interview and pull these out, okay? Because these are not the ones that we use to get to Mars or anything like that. Those are more intense, okay? But let's, so that we'll start the toolbox over here. It's going to be like a box for our orbital mechanics, okay? So, but let's develop some things. Newton's second law. Still exists, right? Don't really need it as part of the toolbox because we know about it. But we are in a circular orbit. So what do we know about the acceleration for things that go in circles? Well, the acceleration isn't changing. The direction is. The velocity is changing. It's centripetal. And do we have a way of writing down centripetal acceleration in terms of, say, I don't know, velocity and radius? V squared over r. Kind of keeps coming back to haunt us, doesn't it? And for something that's in orbit, the one and only force it's acting on is the force of gravity, isn't it? Oops. Big G, mass of the thing being orbited divided by the distance squared. Well, gee, look at that. The mass of the thing in orbit doesn't matter. And we can get rid of one of these r's, can't we? And I can solve this for v. V is going to be the square root of big G, massive thing being orbited, divided by orbital radius. What is that right there? What's that v? It knows velocity. What velocity is it? It's the orbital velocity. This is the speed something needs to have in order to be in a circular path around an object, like, say, Earth, okay? So this speed is the orbital speed, okay? And orbit. And it applies, I mean, if we want to find the orbital speed around Saturn, we want to be we want an orbit around Saturn at a certain distance. What mass do we put in there? Saturn's mass. If we want to be in orbit around the sun, what do we put in there? Sun, Earth. You want to be in orbit around somebody else, but their mass, no, that doesn't work. So this is our orbital speed. But, before I get to the buts, let's just throw in a couple more things into the toolbox. We know how long it takes something to go around in a circle. The distance it travels is the circumference of the circle, and then the time it takes is that distance divided by the speed. This is just, I'm dusting off kind of some old relationships when it came to orbital kinematics, right? So far, our orbital toolbox kind of looks like this, right? It's got these three sort of connected. You could throw in force of gravity, but Force of gravity applies to things in orbit, not in orbit, whatever. This is strictly orbital mechanics. But there's an issue, not an error, just something I need to point out. The orbital speed, how is it related to the distance from the center of the object being orbited? In other words, if your distance from Earth gets bigger, what happens to the speed that you need to be in orbit? It gets smaller, which is exactly like kind of counterintuitive, isn't it? You think like, oh, bigger circle, bigger V. No. That orbital speed goes down the further you go out, right? So where is the fast lane? Is it further away or closer to Earth? It's closer to Earth, which is why the things in low Earth orbit zip around, but the geostationary and other things way out there go much slower. But this brings up part of the weirdness that is orbital mechanics and why people joke about this being rocket science. Let's say you're in orbit around the Earth, and you're in the same orbit as the International Space Station, but you want to catch up to the International Space Station, right? It's ahead of you, a few kilometers. You can see it there, right? Okay. On Earth, if the International Space Station were on the freeway and you were on the freeway, what would you do to catch up? You'd speed up, right? Okay, you'd move faster to catch up with them. Okay, now you're in orbit and you hit the gas. Where are you going? Down. Huh? What do you mean? If I speed up, I go down? Why? Where are the faster orbits? Down, towards the Earth, right? Okay? If you want to slow down, which way do you go? Up. If you want to speed up, which way do you go down? Down. I spoiled it. Even I'm kind of confused now, right? What happens if you fire the engines and point away from the Earth? You're going to slow down. Assuming you stay in orbit. There's ways to break the orbits. Different concept. This is an oversimplification, but the truth is orbital mechanics is weird. It is not intuitive. When our first astronauts got into space, they had trained for this, but it's weird, okay? They were test pilots. They were used to how an airplane flies, right? You increase the throttle, you move forward, you don't go down, okay? When you decrease the throttle, you slow down, you don't go up. They had to relearn how to fly in space, right? And it's a totally different idea. The Russians did a infamous stunt off the International Space Station. The Russians, in order to back in the 90s and early aughts, in order to keep their space program afloat, because the government wasn't funding it, started partnering with companies and advertisers and media personalities to send them to the International Space Station for a few days, film, doing a bunch of stuff, come back, put it on YouTube, that kind of thing. Well, one of the stunts was a sport company that wanted the astronauts to hit a golf ball off the International Space Station, right? Again, part of a media thing. NASA just went to pieces, right? Absolutely went to pieces, because what's a golf ball in orbit? A problem, right? Okay. And so NASA's like, no, you can't do this. And Russia's like, well, we're going to do it anyway. And so NASA's like, okay, wait a second. Let's think about this, right? So I don't think a golf ball has been more studied in the history of our society than it was at that point, because they had to calculate what direction to hit the ball and take into account the fact that somebody in a spacesuit swinging a golf club is probably going to have like a wicked slice or hook, right? Like it's just not going to be accurate, okay? And so they had to compute like all the possible trajectories, right? And the direction to go so that that golf ball eventually would burn up in Earth's atmosphere, right? You wouldn't want to hit it in such a way that it's going to come back 90 minutes later, right? Kind of thing. So yeah, knowing your orbital mechanics is important. By the way, if you ever hear words like prograde and retrograde, prograde means in the direction of the orbit. Retrograde is backwards from the orbit. And then you have other words like periapsis. The periapsis point is the closest point of approach. The way I remember these kind of really long Latin words, peri. Where have you heard peri before? Like think submarine. Not peri the platypus. Periscope, right? Okay. What does a periscope do? Careful. What does a periscope do? Why do periscopes exist? To bring stuff closer, like binoculars, right? We tend to think of periscope, oh, it's a submarine up through the water. That's just mirrors bouncing it around, right? A periscope is named because it brings things closer. Peri means closer to, okay? Apsis is a circle. So periapsis means closest point in the circle, or in this case, ellipse, okay? I think apsis actually means ellipse. So periapsis, and then there is apoapsis. Apo is the other, means further away, okay? So, and then it gets really weird because they'll say like things like perijove and apojove. Jove is the Latin root for Jupiter. So scientists have big fancy words so that we can seem superior over everybody else. But sometimes it's closer to say periapsis than it is to say closest approach to the Earth. Okay, okay. So let's pretend you want to know more, okay? I think the URL might work, maybe not. You can search this up. It's still on the NASA website in spite of the cuts, okay? But the Spaceflight Learner's Handbook, okay? The basics of spaceflight. I know it says the basics of spaceflight. The first page is the basics, then it starts going deep. Like, they said it's written for like high school level. It's not, okay? The JPL engineers got way too happy about this. But there's lots of information about how to do this for reals. I can highly recommend this program. Not Kerbal Space Program 2. That was a dumpster fire, okay? But, and a big disappointment for me. I was so excited about that release, and then it went nowhere, okay? But Kerbal Space Program I think it's a wonderful learning tool about orbital mechanics, right? The conceit is that you are controlling the Kerbals, these cute green people, and they are trying to get into orbit around their planet and go to the moon and do all these different things, right? And it teaches, the game is build the rockets, like engineer, you get to actually build the rocket parts, and then you try to launch them and they blow up and nothing works. And then eventually you learn what works and what doesn't, okay? And the joke kind of is that Elon Musk is playing Kerbal Space Program IRL, right? So it's one I can recommend. Now, I want to play this video for you. I do want to make it very clear that I don't like Elon Musk, okay? I used to, okay? But I can't agree with his politics or his morality anymore, right? So I don't support the man. But as far as I'm concerned, SpaceX, right, like the company and the engineers and the people and what they're trying to do is absolutely incredible. They are pushing the boundaries of what engineers can do in aerospace, and I think it is, quite frankly, amazing, okay? They are just knocking, they are so far ahead of everybody else, it's not even funny, okay? So I want to show you this video, okay, right? Because when the history books are written, okay, and we, 200 years from now are living on the surface of the moon or Mars or something like that, okay, and they go back and say, when did it all start? Like, what was the inflection point? I think it was this. Now, what you are about to see was the very first launch of what's called the Falcon Heavy. This is not the Starship, the big one that they're launching right now. This is a few years ago. And the Falcon Heavy consisted of 3 rockets, duct taped together, launching stuff, okay? The 2 boosters on the side returned to the launch site.
And watch for the landing legs deploy at the tail end of that landing leg.
We'll keep it down. So what you're seeing here, booster, return, to the cameras on the boosters. There's the landing pad. Look at the upper left. Watch the upper left.
Towards their respective landing zones.
Watch what happened.
Star boosters landing legs are deployed.
We live in Star Trek.
Have landed.
Okay? The absolute gobsmacked expression on people's faces when they first saw this cannot be understated. SpaceX has made it feel routine now, right? I think their booster that's landed, it's like 29 now. The booster that's got the most landed is like at 29 or 30 or something like that, okay? Crazy making, okay? Everybody told SpaceX that they were nuts 10 years ago. You can't land a rocket. Okay? How did they do it? This is how. This is a SpaceX video, by the way. So how did SpaceX do it? They learned all the wrong ways to do it, right? That's always been something I've been teaching you, right? How do you learn? Fail fast, right? Because you start learning from your mistakes and you'll get there. I will see you Tuesday where we'll finish up chapter 13 and start chapter 14.